Okay, everybody, welcome back. Hopefully you've given your brain a little bit of a rest. Let's carry on with shapes, and then we'll see what you can do with the information we've just learned. Firstly, I have something cool that you guys and girls can do at home, and it's going to look, you might think it's a bit silly, we're in grade 11, we're too cool for school. This is cool, you get to eat them afterwards. What I've done is I have made shapes using jelly tots and toothpicks. So it might not look very big to you right now. And that's okay. And yes, there are really fancy chemical sets that we can use, but I like these because I like jelly tots and then I can eat them at the end. So that's cool. If you are having problems visualizing, getting this picture into your head because you're just looking at a screen or you're looking at a book, get yourself a small packet of jelly tots and some toothpicks or just some sticks. It doesn't matter what you use. And make each shape. And then you can see how the atoms are arranged. So this one here is a linear. I've got a central atom, I've got one in the middle, and then I've got two on the outside. There's no lone pairs around it. Remember, we said these shapes have got no lone pairs. And it's linear because it's in a straight line. The furthest away that these two can be from each other is on opposite sides of this middle atom. Right? So once I've done that, what can I do? I can eat my jelly tots. What about the next one? I've got trigonal planar. So let's have a look at the next one. How do I make a trigonal planar molecule? So I've got one here. All right. It's hard to see. I know I'm trying to hold it in a way that you can actually see what's going on. Again, I've got a central atom, and these happen to be three atoms that are the same. And they are as far apart from each other as possible. The reason I like doing this, besides jelly tots, like I said, is you can see that this is three-dimensional. Okay, and atoms and molecules are three-dimensional. When we look at them on a screen or we look at them on a page, we just see them in one dimension, and sometimes our brain doesn't always understand what we need to understand. When you see it like this in 3 dimensions, then you can understand the bond angles or the angle between atoms. So here we've got an angle, and we could measure it if we wanted to. The best angle of separation for those three would be 120 degrees. Why? Because a circle is 360 degrees, and I need to split my circle into 3. So 360 divided by 3 is going to give me 120. So my best angle here is going to be 120 degrees, right? But now I can see it in 3 dimensions. What about my next one? Tetrahedral. Because this one, I don't know what you think, but I think this one looks pretty funny. Because sort of got the 3 sort of sitting in the front, and then got this funny thing sticking up. To me, that doesn't look like it's a shape of 4. Okay? But if I build it, I'm then able to see what is actually happening. Right? Let's see if I can get it to rest on my palm. So I've got my central atom, and you'll see I'm using jelly tots that are a similar color because I'm just using molecules, simple molecules that are made up of one atom and then 3 or 4 other atoms that are the same, right? So I've got my central atom, and I've got my 4 other atoms spread as far apart from each other as possible. And it doesn't matter which way around I turn these, I can always measure the angle, and I can always figure out and find the correct angle. Okay, so that is our tetrahedral. Remember, tetra is 4. That's our tetrahedral molecule. What about our trigonal bipyramidal? Because this one, I don't know, this one also looks complicated. So for me, like I said, I like building these things. So here we go. This one looks a little bit squashed because I had it lying down, but again, I've got my central atom, and then in 3 dimensions, I've got 1, 2, 3. Those 3 are planar. Those 2 at the top and that one at the bottom, are planar. So they actually are arranged like this one was, okay? But at the same time, I've got these other 2, one side, that are arranged like a linear molecule. So what I've got here is I've got a combination of linear and trigonal planar. And those two together are going to make up trigonal bipyramidal. Now, why is it called bipyramidal? Okay, so trigonal because of this 3 in the middle, and then pyramid here. If you can imagine lines drawn from there to there, then from there to there, there to there. You've got a little pyramid sitting on the top. If I turn it upside down, I've got another little pyramid. So bipyramidal, so 2 pyramids, one on top, one at the bottom. Okay? And our last one. And I'm sorry, I'm going to have to eat the jelly tarts just now when we have a break. So you'll have to get yourselves one so that you can eat your own jelly tarts, because I know I'm going to make you jealous. So sorry about that. Last one is my octahedral. Okay? So what have we got going on? Let's look at it at different angles. In the middle, I've got a central atom. Top and bottom, I've got linear happening. Okay? Top and bottom, I've got linear happening. What is happening in the middle in this horizontal plane? So in the horizontal plane, I've got 1, 2, 3, 4 of them. Okay? So if I wanted to draw lines, what I would do is I would actually be able to create an octahedral shape. So you know an octahedral, 8-sided shape? So if I was going to draw lines that are going to be joining all of these together, I'm going to draw a beautiful octahedral shape. And that's why this has got the name octahedral. Okay, so again, really nice. I can look at it in 3 dimensions. So like I said to you, looks really tiny on the TV, I know. Do yourself a favor, get together a group of buddies, just save up some pocket money or ask your mom, get some jelly tarts, get some toothpicks, do it for yourself. Okay, and then your reward afterwards, once you've learned it, is that you get to eat the jelly tarts, which I think is pretty cool. Let's move on. So I've done all the talking and I've done all the theory. Now I want you to do some work. And what I've got for you here is a Lewis diagram. Now I know you're going to say to me, but we did Lewis diagrams in grade 10 and I really don't need to know a Lewis diagram, and it doesn't matter. Lewis diagrams are really, really important for this section. So what I'm going to do is I'm going to give you 2 minutes. You are going to draw a Lewis diagram for beryllium, Lewis diagram for chlorine, and a Lewis diagram for the beryllium chloride molecule. Hopefully you've got a periodic table in your book or somewhere in the classroom. Okay, if you don't and somebody else has got, see if you can share with them. Use your periodic table if you need to. Draw your Lewis diagrams, and then I will go through it with you step by step. So I'm giving you 2 minutes this time. 2 minutes to draw these things starting now. Okay, everybody, time's up. But just quickly, before I go on to answer these questions, I didn't think that green would be a problem, and I made my little shape using green jelly tots. So just to make sure that you've seen the jelly tots and to make sure you've seen the shape, I'm just going to go back and show you octahedral again. So it's the one at the bottom here, and hopefully now you can see the colors. So if you couldn't see them, I'm sorry. Our background is green, and I forgot that I need to have colors that you can see. So once again, we've got our central atom. Remember, we've got our linear top and bottom. Okay, so linear going up and down like that. And then in our horizontal plane, I'm going to tip it slightly. In our horizontal plane, we've got 1, 2, 3, 4. So we've got like a tetrahedral, but it's in one plane. Okay? And if I wanted to figure out where the name octahedral came from, remember what I said to you? Just draw the lines from each atom to the next, okay? And you're going to get your octahedral shape. So hopefully now, I'm sorry about that again, hopefully now you will be able to see what I mean by octahedral. And then I think as a reward, you can definitely eat these, seeing as I got the wrong color. Right, let's go back to the question that I said to you. So Lewis diagrams. Remember, we need our valence electrons, so those electrons in the outermost energy level. And I'm going to draw beryllium for you. So beryllium is Be. And hopefully you are telling me now that beryllium has got 2, 3, 4. Can anybody, how many valence electrons does beryllium have? Beryllium is in group 3, group 4. So beryllium, we're going to have, if I can get this to draw, two. So I've got 1 electron on the top and 1 electron on the side. Some people want to draw it like this, where you've got beryllium with an electron on either side. It doesn't matter. Okay, right now you can draw it either way. I know some people are very strict. Some teachers are strict that they want you to draw it according to the orbitals, so 2 at the top and on you go like that. You just need to answer according to how your teacher wants you to draw it, okay? But as far as I'm concerned, I think as most teachers, all 3 of these are acceptable. So let's look at the chlorine. Chlorine's in group 7. I'm going to use a different color for the electrons, just so that they stand out. And if you want to, you can use dots and crosses. So chlorine has there got 7 valence electrons. So now if I'm going to draw the beryllium chloride molecule, remember I write Be and I write my Cl. Put my electrons in place. There's 1. And there's my 1 from my beryllium. And on the other side, I mustn't forget my other chlorine. Seven, and my little electron from beryllium. So our molecule that we have here is going to be a linear molecule because it's all in a line. And what do we notice about our central atom? Our central atom has got no lone pairs. So this is why it's a linear molecule with no lone pairs. I might have lone pairs in my chlorines, that's fine. But my central molecule has got, or my central atom has got no lone pairs. So now, I want you to have a look at this, because what we're going to do when we come back from the ad break is you are now going to try and do the same thing using your Lewis structures to determine the shapes or the molecular geometry. Okay, so I'm going to send you off on a break. Again, you can have a bit of a brain break, get some fresh air into your head. breathe a little bit, stop panicking about all the big words that we've been using, and I will see you shortly. So go and have a break. I will see you soon.